Students, so welcome back to my video lecture 5 on p block elements. So what was that we are talking in the last video? We were talking about the trihalides of boron family, isn't it? So I told you all the elements of boron family reacts with halogens to form trihalides except thallium, which reacts with halogen to form only monohalide, isn't it? So from boron to indium, that is from boron to indium, they all will form trihalides, like boron trihalide, yes, aluminium trihalide, gallium trihalide and indium trihalide. Whereas thallium will form monohalide of the type TLX, because thallium is more stable in +1 oxidation state due to inert pair effect. Due to inert pair effect. Understood? Now at last I think I was talking about the acidity of the trihalides of boron, isn't it? Now trihalides of boron, yes. So please refer to my previous video. Hope you have watched my previous videos and then you are watching this fifth video. If you directly watch the fifth video, no, you will not have any connection, you will not have any bridge. So if you want to understand the concepts of this video, you should be well versed with the concepts of the previous videos. So now I am talking about the trihalides of boron. So guys, which are the trihalides of boron? We have boron trifluoride, boron trichloride, boron tribromide and boron triiodide, correct? I told you that all these trihalides of boron are Lewis acids, isn't it? They are Lewis acids. Why they are Lewis acids? Because in all these trihalides, boron is electron deficient. In trihalides, boron is surrounded by only 6 electrons, correct? 1, 2, 3, 4, 5, 6. So the central atom boron is surrounded only by 6 electrons. It requires 2 more electrons to complete its octet. Hence it is it is electron deficient. It is ready to accept the electron pair. Hence it acts as a Lewis acid. So all the trihalides of boron are Lewis acids. But what about the order of acidity? I told you boron triiodide is a strong Lewis acid than boron tribromide, which is a strong Lewis acid than boron trichloride, which is further strong Lewis acid than boron trifluoride. So boron triiodide is a strong Lewis acid, whereas boron trifluoride is a weak Lewis acid. But why is this? I think I was in a process of explaining why boron triiodide is a strong Lewis acid and why boron trifluoride is a weak Lewis acid. We shall understand this with the help of their structure. Why boron trifluoride and boron trichloride, they are weak acids? Because boron trifluoride and boron trichloride, they involve in something called as back bonding. So because of back bonding, boron trifluoride is going to be a weakest Lewis acid. Because of which bonding? Back bonding. But there is nothing like back bonding in boron triiodide and boron tribromide. They will not undergo back bonding. There will be no back bonding in these two cases. Hence they are going to be a strong Lewis acids. They're going to be a strong Lewis acid. Let us understand how boron trifluoride and boron trichloride undergo back bonding and what exactly is this back bonding. Understood? Yes. Now if I consider boron trifluoride, understand this point. Boron trifluoride, BF3, boron trifluoride. I told you, look at the atomic number of boron. What is the atomic number of boron? It's 5. What is its electronic configuration? 1s2, 2s2, 2p1, isn't it? So in 2s orbital, there are 2 electrons. and in 2p orbital there is 1 electron, correct? There is 1 electron. Now boron will undergo excitation. Boron gets excited. When it gets excited, it will transfer one of its s electron to p orbital. Okay, when boron gets excited, okay, it will transfer one of its s electron to p orbital. Look at here. Yes, okay, it will transfer one of its s electron to p orbital like this. P orbital. I told you that in all the trihalides, boron is sp2 hybridized, isn't it? It will use one s orbital and two p orbital, and it will undergo what type of hybridization? sp2 hybridization. Therefore the shape is trigonal planar. Look here, there is one vacant p orbital which is unhybridized, correct? This vacant p orbital will not be involved in hybridization. Okay, this vacant p orbital will not be involved in hybridization. Understood? Okay, now come back to boron trifluoride. Look at boron trifluoride here. Boron will undergo what type of hybridization? sp2 hybridization, and it forms 3 bonds with fluorine. It bonds 3 bonds with what? Fluorine, and there will be one vacant p orbital in boron. One vacant p orbital in boron, isn't it? Okay, yes. Now, okay, so which vacant p orbital is it? It's 2p vacant p orbital, correct? It's 2p vacant p orbital. There is vacant 2p orbital in boron. Now, we know fluorine has 3 lone pair of electrons. It will have 3 lone pair of electrons. All the fluorine atoms will have 3 lone pair of electrons, correct? Okay, you can consider the atomic number of fluorine. What is the atomic number of fluorine? 9, isn't it? What is its electronic configuration? 1s2, 2s2, 2p5. Is it correct? 1s2, 2s2, 2p5. There are 2 electrons in s orbital, okay, 2s, and there are 5 electrons in 2p orbital like this. 1, okay, 2, 3, 4, 5. Okay, look here. 1 lone pair, 1 lone pair, 1 lone pair, isn't it? Okay, so there are lone pair of electrons in 2p orbital and 2s orbital of fluorine, isn't it? So fluorine has lone pair of electrons in 2p orbital. Okay, this is the vacant 2p orbital of boron. Now what is going to happen here is fluorine will transfer its lone pair of electrons from 2p orbital to the vacant 2p orbital of boron. It will transfer, okay, its lone pair of electrons. Look here. So fluorine will transfer lone pair of electrons from its 2p orbital to the vacant 2p orbital of boron, and it forms a coordinate bond. When fluorine transfer the 2 electrons, okay, from its 2p orbital to the vacant p orbital of boron. Now how many number of electrons around boron? 2, 4, 6. Now it has got 2 more electrons from fluorine. So don't you think the octet of boron is complete? When the octet of boron is complete, is it ready to accept the electrons? No, it will not be ready to accept the electrons. Hence, boron trifluoride is going to be a weak Lewis acid. Weak Lewis acid. Understood? Are you able to understand my point? There will be, once again I repeat, please note this point, please be careful, understand the concept very well. Okay, there will be one vacant 2p orbital in boron. Okay, after hybridization there will be one vacant unhybridized 2p orbital in boron. Fluorine has lone pair of electrons in 2p orbitals, isn't it? Fluorine has lone pair of electrons in 2p orbitals. Now 2p overlapping will be very good. Okay, if the 2 orbitals have same energy, the extent of overlapping will be strong. Is that correct? Okay, now what is it happening here is, so fluorine will transfer its lone pair of electrons from its 2p orbital to the vacant 2p orbital of boron, okay, and it forms a coordinate bond. When fluorine transfer its pair of electrons to boron, okay, now octet structure of boron will be complete, isn't it? Look at, count the number of electrons around boron. Okay, 2, 4, 6, 8. When the octet structure of boron is complete, okay, do you think boron is ready to accept few more electrons? No, boron will not accept few more electrons. When boron does not accept electrons, it's going to be a weak Lewis acid. It's going to be what? Weak Lewis acid. Any doubts? Are we clear with this? Okay. Now, if you consider boron triiodide, if I consider boron triiodide, okay, observe here what is going to happen in boron triiodide. What will happen in boron triiodide? Observe the case. Okay, see iodine. Okay, iodine. So it will have the outer electronic configuration of iodine as 5s2. Okay, yes, 5p5. 5s2, 5p5. Okay, there are 2 electrons in 5s orbital and 5 electrons in 5p orbital. 1, 2, 3, 4, 5. Okay, now if you consider iodine, the lone pair of electrons are in 5p orbital, isn't it? Okay, if you consider iodine, okay, the lone pair of electrons are in which orbital? 5p orbital. Okay, but now the vacant, which is a vacant orbital of boron, it is 2p. 2p and 5p. There is large energy difference between 2p orbital and 5p orbital, isn't it? Since there is large energy difference between 2p orbital and 5p orbital, okay, iodine cannot transfer its lone pair of electrons to boron and form a coordinate bond. So here iodine cannot form a coordinate bond. Iodine cannot transfer its lone pair of electrons to the vacant p orbital of boron. Why? Because the energy difference between 2p orbitals to 5p orbital is more. Okay, see, in chemical bonding we have learned, okay, if the 2 orbitals has to overlap, okay, if the 2 orbitals can overlap only when they almost have same energy, okay, only when they have almost same energy. But here the 5p orbital of iodine cannot overlap with 2p orbital of boron. Why the 5p orbital of iodine cannot overlap with the 2p orbital of boron? Because they have large energy difference. Since there is large energy difference, this 5p orbital of iodine cannot overlap with the 2p orbital of boron. Hence iodine cannot transfer its lone pair of electrons to the vacant p orbital of boron. So when iodine cannot transfer its lone pair of electrons to boron, boron again becomes electron deficient, isn't it? It will be surrounded by only 6 electrons, isn't it? 1, 2, 3, 4, 5, 6. Is that correct? Okay, so boron will be surrounded only by 6 electrons. It becomes electron deficient. When it becomes electron deficient, it is ready to accept the electrons. When it is ready to accept the electrons, it is going to be a strong Lewis acid. Okay, that means there is no back bonding in iodine. Okay, whereas there was back bonding in fluorine. Correct? Okay, why there was back bonding in boron trifluoride? Because 2p orbital of boron and 2p orbital of fluorine, they have same energy, they can overlap. Okay, there will be back bonding in boron trichloride. Why? Because 2p orbital of boron and 3p orbital of chlorine, almost same energy, but there will be no back bonding in boron tribromide and boron triiodide. Why there is no back bonding? Okay, if you consider boron tribromide, okay, 4p orbital of bromine should overlap with 2p orbital of boron. There is large energy difference, there will be no back bonding. If you consider boron triiodide, okay, 5p orbital of iodine should overlap with the 2p orbital of boron. No, there is again a large energy difference. When there is large energy difference, there will be no back bonding. When there is no back bonding, boron will be deficient of electrons. If it is deficient of electrons, it is going to be a strong Lewis acid. Okay, it's going to be a strong Lewis acid. That is why boron trifluoride is a weak Lewis acid. Okay, because in boron trifluoride there is back bonding and the electron deficiency of boron is reduced by fluorine, whereas in boron triiodide it is going to be a strong acid. Why? Because there is no back bonding. Since there is no back bonding, boron becomes electron deficient and it is ready to accept electrons. That is why it is going to be a strong strong Lewis acid. So what is the order of Lewis acid nature? Okay, yes, of course, boron triodide is a strong Lewis acid than boron tribromide, which is a strong Lewis acid than boron trichloride, and then boron trifluoride. This is a weak Lewis acid because of back bonding. Okay, since there is overlapping of 2p orbital and 2p orbital, here also there is overlapping of 2p orbital and 3p orbital, but here there is no overlapping because of 2p and 4p. Here also there can never be overlapping because of 2p and 5p. Okay, yes, if there is large energy difference between the orbitals, those orbitals cannot overlap, they cannot form bond, they cannot exchange electrons. Only when the two orbitals have same energy, they can form bond, they can overlap, and they can exchange what? Electrons. They can exchange electrons. Hope you have studied that in chemical bonding. Understood? Okay, that's correct. Okay, I hope you have understood this. That's fine. Okay, next one. Hydrolysis of halides of boron. Hydrolysis of halides of boron. Yes, okay. Hydrolysis of halides of boron. Hydrolysis of halides of boron. Okay, observe here. So we have different trihalides of boron, which is at boron trifluoride, boron trichloride, boron tribromide, boron triiodide, isn't it? Okay, observe here. What do you mean by, okay, hydrolysis? Reaction with water, isn't it? Hydrolysis is nothing but reaction with water. Is that correct? Look, boron trichloride, boron tribromide, boron triiodide, these three will undergo, okay, complete hydrolysis. They will undergo what? Complete hydrolysis. Complete hydrolysis. Whereas boron trifluoride, this will undergo partial hydrolysis. This will undergo partial hydrolysis. Boron trifluoride will undergo partial hydrolysis, whereas boron trichloride, boron tribromide, and boron triodide will undergo what? Complete hydrolysis. Complete hydrolysis. Okay, what do you mean by partial hydrolysis? Okay, see, out of 100 molecules of boron trifluoride, only 80 molecules will undergo hydrolysis. Will undergo what? Hydrolysis. That is what we call partial hydrolysis. Whereas here, all the 100 molecules will undergo hydrolysis, all the 100 molecules will undergo hydrolysis, and all the 100 molecules will undergo hydrolysis. That is what I call complete hydrolysis. Okay. Now, what happens when boron trichloride, boron tribromide, and boron triiodide are hydrolyzed? Look here. Okay, hydrolysis means reaction with water, isn't it? Boron trichloride reacts with water. Okay, boron tribromide reacts with what? Water. Okay, and boron triiodide reacts with water. Okay, how do they react with water? Very simple. Whenever you are writing the reaction in ionic form, you just have to exchange what? Ions, isn't it? In boron trichloride, what are the ions? Boron in +3 state and chlorine in -1 state, isn't it? And in water we have H plus and OH minus, isn't it? Okay, what you are supposed to do? You are supposed to interchange the ions. That's it. Okay, you are supposed to interchange the ions. Yes or no? Okay, so that means B3 plus ion will combine with OH minus ion, and H plus ion will combine what? Cl minus ion. And what about the formula of the compound that is formed here now? Okay, again crisscross method. Multiply +3 charge to hydroxyl and -1 charge to bromine. So this is going to be what? BOH thrice. H plus Cl minus will combine to form what? HCl, isn't it? So therefore I can say boron trichloride reacts with water to form what? Okay, boric acid plus HCl, isn't it? boric acid plus HCl. Like that, boron tribromide reacts with water to form what? Boric acid plus HBr. Okay, yes, boron triiodide reacts with water to form what? Boric acid, okay, plus hydrogen iodide. Understood? Okay, hope it is clear. Boron trichloride reacts with water to form boric acid plus HCl. Boron tribromide reacts with water to form boric acid plus hydrogen bromide, and boron triiodide reacts with water to form boric acid plus hydrogen iodide. Okay, so please hope you can know, okay, simple method to write the reaction. Yes, are we clear? Okay, simple. You just have to interchange the ions. B3 plus, positive ion of this one will react with negative ion of this one. Okay, negative ion of this one will react with the positive ion of this one. Correct? Okay, just interchange the ions. Okay, apply crisscross method and get the product. Okay, no doubts. Then what happens if, okay, boron trifluoride undergo hydrolysis? By the way, I told you boron trifluoride will undergo partial hydrolysis. Okay, so what happens when boron trifluoride is hydrolyzed? Okay, hope you can remember this. When boron trichloride or boron tribromide or boron triiodide is hydrolyzed, they all will form what? Boric acid along with HCl, HBr and Hi. Okay, but if boron trifluoride undergo hydrolysis, look at here. If boron trifluoride undergo hydrolysis, see this, okay, it will form one more product. Okay, one more product. What is this? Okay, when it undergo hydrolysis, no doubt it is going to form boric acid, BOH thrice, plus it will form hydrogen fluoride plus BF4 minus. Okay, one product extra. Understood? Okay, so when boron trifluoride reacts with water, it forms boric acid, hydrogen fluoride, okay, along with what? BF4 minus. Okay, boron tetrafluorate, BF4 minus. Understood? Okay, so are we clear with all these things? Boron trifluoride, boron trichloride, boron tribromide and boron triiodide. No doubts with this. Now let us understand the trihalides of aluminium. Trihalides of aluminium. Okay, now let us talk about the trihalides of aluminium. Okay, trihalides of aluminium. Understand this point here. Okay, what are the different trihalides of aluminium? See, one is aluminium trifluoride, aluminium trichloride, aluminium tribromide and aluminium triiodide, isn't it? Okay, aluminium trifluoride, aluminium trichloride, aluminium tribromide and aluminium triiodide, isn't it? Okay, see, note one point here. See, okay, trihalides of boron family, we know trihalides of boron family are electron deficient. Is that correct? I showed in terms of boron trihalides, correct? Boron trichloride, boron trifluoride, boron triiodide, boron tribromide are all electron deficient because boron will be surrounded only by 6 electrons. They are electron deficient, that is why they are Lewis acids, isn't it? Okay, so if you consider trihalides of any element, so the trihalides of boron family are electron deficient, isn't it? Electron deficient, no doubt in it. Even the trihalides of aluminium are also electron deficient. Okay, yes. Now see, they try to satisfy the electron deficiency, okay, either by first one, okay, back bonding, either by back bonding, which we learnt in case of boron trifluoride and boron trichloride, correct? Okay, so there in boron trifluoride and boron triiodide, don't you think the electron deficiency of boron is satisfied because of back bonding by fluorine and chlorine, correct? Okay, so they try to satisfy the electron deficiency either by back bonding or by, okay, or else by what, dimerization, or else by dimerization. Understood? Yes. So all the trihalides of boron family are electron deficient. They try to satisfy the electron deficiency either by back bonding or by dimerization. Now if we go with the trihalides of aluminium, if I talk about the trihalides of aluminium, look at here, the trihalides of aluminium, they cannot, okay, they, all the trihalides cannot, okay, cannot form back bonding, cannot form what, back bonding, okay, they cannot form back bonding. Now they can only undergo what, they can only undergo dimerization. They can only undergo what, dimerization. Okay, so they cannot form back bonding, they can only undergo what, dimerization. So all these trihalides of aluminium, they cannot form, okay, what, back bonding. Why they cannot form back bonding? Look here, okay, if I consider aluminium, okay, yes, aluminium will have 3p orbital as what, vacant orbital. We know fluorine has lone pair of electrons in 2p. Okay, here also aluminium 3p, chlorine 4p. Okay, 3p, yes, okay, sorry, 3p, and here 3p 4p, 3p 5p. Okay, understand this point. Since there is large energy difference between 3p 2p, 3p 4p and 3p 5p, there can never be what, back bonding. Hence they can, now these trihalides of aluminium can only satisfy their electron deficiency through which one, dimerization. They can never undergo back bonding. Why they can never undergo back bonding? Because in aluminium trihalides, which vacant orbital of aluminium is involved? Okay, 3p vacant orbital of aluminium is involved. Hence, okay, there is large energy difference between 3p 2p, 3p 4p and 3p 5p. Therefore they can never be what, back bonding. They can satisfy their electron deficiency only through dimerization. Understood? Okay, now look at how aluminium trichloride undergoes dimerization. Observe this phenomena here. Okay, usually aluminium trichloride, AlCl3, will not exist as one molecule. It exists in the form of what, Al2Cl6. It exists in the form of what, Al2Cl6. That means, okay, now it will, now two molecules of aluminium trichloride will combine to form one molecule. How do they combine? Observe this, aluminium, okay, yes, aluminium trichloride, AlCl3. Observe this, aluminium trichloride, correct? Aluminium trichloride, AlCl3, isn't it? Okay, now yes, this has lone pair of electrons. Okay, this has lone pair of electrons. Aluminium has vacant orbital. Aluminium has what, vacant orbital. Now this chlorine will transfer its lone pair of electrons to the vacant orbital of aluminium and it forms a bond. Therefore there is a bond between what and what, aluminium and chlorine. Okay, so here also the lone pair of, now this chlorine will transfer its lone pair of electrons to the vacant orbital of this aluminium and it forms a bond. Hence there is a bond between what and what, aluminium and chlorine. Okay, so there is a coordinate bond between aluminium and chlorine. There is a coordinate bond between aluminium and chlorine. Okay, therefore these two molecules will exist together. Okay, so two molecules are combining to form what, one molecule. That is why this is called as what, dimer. What is this called as? Dimer. Understood? Okay. Therefore, don't you think now, since when chlorine transfer its lone pair of electrons to the vacant orbital of aluminium, okay, the electron deficiency of aluminium will be satisfied, isn't it? Okay. Here also, when chlorine transfer its lone pair of electrons to aluminium, the electron deficiency of aluminium is satisfied. Okay. So therefore, the trihalides of aluminium will satisfy their electron deficiency only through what? Only through dimerization. Through what? Dimerization. Okay students, so I hope you have understood all about the trihalides of boron and the trihalides of aluminium. I hope you have understood what is back bonding and what is dimerization. So in the next class we will solve some MCQs from MTG fingertips. Okay, thank you.